Sneemaster!
Hi everyone, Sneemaster here to discuss how engines and thrusters might feasibly work in Star Citizen. There isn't much information online about the technology used that I can see, and CIG has been sort of vague on it. In Star Citizen, engines are split into two parts, the power supply and the thrusters. The power supplies, according to the wiki, are generally either fission reactors, fusion reactors, or antimatter, but there could be other alternatives. The power supply power the plasma thrusters as well as the shields, weapons, and other electrical systems. For the power supplies, I've noticed that currently we don't have any fuel needed for them, so how do they run? Is this a temporary thing, or will all reactors not require fuel? Fusion and antimatter reactors would definitely require a constant influx of fuel. Fission reactors can be filled with a fuel when installed and would last for years potentially. Current nuclear aircraft carriers and submarines only refuel about 7 to 10 years, so maybe all generators are the same? Who knows? Fission reactors work by bombarding an atom with a very high neutron count with a slow or fast neutron, depending on the fuel. For example, uranium-235 is an unstable atom due to all the neutrons in it, and tends to absorb slow neutrons. The neutron gets absorbed and causes the already unstable atom to split apart into smaller pieces, plus giving off more neutrons and some radiation and heat. These other neutrons then hit more fuel, and the process continues in a chain reaction until the fuel runs out. The heat from the reactions and the decaying particles is used to power devices. The speed of the chain reaction can be sped up or slowed down by changing the speed of the neutrons using materials like graphite. The main problems with fission reactors would be neutron shielding, converting to energy, cooling systems, and radioactive fuel and waste in explosions or damage. First of all, current fission reactors use neutrons to initiate the reactions and create chain reactions, which spit out more neutrons. Neutrons are particularly dangerous to life and items around us. When one or more loose neutrons hit an atom, they can be captured and it can cause the atom to be unstable, which can cause two issues. One, the extra neutron can make the atom react differently in molecules. For example, deuterium, which is hydrogen with an extra neutron, can poison you if you drink water made up of it. Second, the atom can also decay and emit other radiation such as alpha rays, beta rays, X-rays, or gamma rays. That radiation is called ionizing radiation that can knock electrons out of other atoms, which also can cause atoms to no longer bond with other atoms in molecules, causing very bad effects such as cancers, or making the molecules poisonous, or have a weaker bond. Living cells can die, and metals can become brittle and weak. Normally, dense materials are used to shield neutrons, like lead or multiple thin layers, or different materials, but both can get heavy and aren't always very resistant to damage. That's not very great for spaceships, especially in a small fighter if the reactor is right behind you. Second, fission reactors generate a lot of heat from the fission reactions. Turning the heat into electricity is vital to the whole process. Current systems normally heat up water into steam and run turbines. This would be difficult in spaceships as water is heavy and steam requires sturdy systems in place. All the moving parts would require a lot of maintenance as well. We could instead use thermoelectric systems using the Seebeck effect, where a temperature change, hot on one side, cool on the other, causes an electric potential. Another option is we could use Stirling engines where a piston is moved by the temperature change, and the piston movement creates an electric charge in a magnetic field. You do have moving parts, but possibly less complicated or expensive than a steam turbine, but it could go either way. Either way, we need a cool side for all these processes to work. This leads to how do you cool all that heat for the energy to be useful and to not explode. Normal Earth-based reactors have those giant cooling towers, but that wouldn't work in space. Spacecraft currently have those long radiators that look like solar panels. They emit infrared waves out into space to cool the ships. As you can see, the radiators are huge compared to the ship, and that's without even using nuclear reactors. I don't see those on Star Citizen ships, but maybe they just ignore it for the rule of cool, no pun intended. Also, the infrared signal would be very noticeable. Another option is to transfer the heat to already cool particles, like stored liquid hydrogen, and emit that from the ship, which would boil off like evaporative cooling. Those heated particles would also show up, but it would take less space, and be less delicate. Of course, you'll have to carry the coolant with you and refill it often, so we'll need a coolant refueling system if that's the case. Finally, what happens when a ship explodes or a reactor containment fails? Fission reactors would spew radioactive material everywhere. It would be bad for the crew inside of a ship, and really bad for life in the atmosphere of a moon or planet. Fission fuel and waste can be radioactive from seconds to millions of years, depending on the fuel. They have a decay rate that varies, depending on the particle. Maybe Star Citizen ships have little vacuum systems in case of a breach that sucks up all the radioactive fuel and waste and stores it in a box. We have seen some radioactive waste missions so far, so maybe that's part of it. Now, fusion reactors, on the other hand, don't focus as much on neutrons. They mash two atoms together of different types, like deuterium-deuterium, deuterium-tritium, lithium-hydrogen, or boron-hydrogen, to make a new larger atom that is generally unstable. That new atom releases either alpha particles, energetic helium atoms missing electrons, beta particles, which are electrons or positrons, or gamma rays to become more stable. We can convert these particles or rays to electricity more directly. Alpha and beta particles are charged particles, so a magnet can convert their kinetic movement to electricity. Gamma rays are like light, and you can theoretically use a solar panel type of system, photovoltaic, to convert that to electricity. There is also heat involved, both in containing this hot plasma energy, and then in the resultant particles flying around. Even the magnets get really hot, so we still have the cooling issue. Luckily, that excess heat can also be converted to electricity, like the fission system earlier, but also requiring cooling systems like before. There are different methods for fusion, such as magnetic confinement, blasting fusion fuel with lasers, slamming ion streams at each other, or even some sort of combination, and I'm sure there may be more in the future. Luckily, there is less neutron radiation emitted with fusion, or with some fuels, none at all. That's called aneutronic fusion. So shielding would be less, but you would need a constant stream of fuel. So maybe the hydrogen fuel intakes on the ships is both for the fusion reactors and the propellant for the engines? That might make sense with a lithium proton system or boron proton system. Just store a bunch of lithium in a solid liquid form, then smash it into ionized hydrogen gas that you scooped up. If not, then we need a way to refuel the fusion reactor as well. There are also more exotic systems like antimatter reactors, or maybe even mini black hole reactors. With antimatter, you can take matter and antimatter of the same type and opposite charge and mash them together to release pure energy. Simple electrons and positrons, which are anti-electrons, release pure gamma rays, which we can convert to electricity with photovoltaics. Probably many layers of them, since gamma rays tend to travel through materials easily. Heavier matter and antimatter reactions often give off a mix of exotic particles, like muons or other things that have short lifetimes, and they will decay to more conventional rays particles that we can use for power, but would be messier. The problem is you need very powerful magnets to contain the antimatter until it's ready to be used. That can be heavy and very hot, and delicate. The nice thing is antimatter is super efficient and only needs a tiny amount. I believe 1 gram of antimatter can power a Saturn V rocket into space. If you can store it safely, then you could easily carry fuel to last months or years, like fission. Any containment failures would make a very large explosion, like we've seen in combat. Creating the antimatter might be very expensive unless they find some cool new future method of making it in Star Citizen. Typical creation of antiparticles involves accelerating normal matter at high speed into other particles, such as electrons into a gold foil target in a vacuum. It takes a lot of energy to accelerate the electrons, and that excess energy is turned into positrons. Then we use magnets to separate the particles and store them. If we could somehow collect cosmic rays from space that already have that much energy, then maybe we could make antimatter easily that way. Your ship would need to at least have minimal power on at all time for the antimatter storage not to explode. So it might be possible, but we'll have to see. You could use mini black holes instead. They could be created if you compress material dense enough, maybe with lasers and magnets. Small black holes with any mass less than a planet would fall apart pretty quickly, if Stephen Hawking is right about his Hawking radiation, and that would release a lot of pure energy. Hawking radiation is believed to be emitted in thermal form from black holes that are not absorbing material and are small enough. The smaller the black hole, the more Hawking radiation it emits, which causes it to shrink further, and so on until the black hole disappears. The only problem is the heat released might not be very much, but it could be converted to electricity. This would require even more powerful magnets or lasers and a lot of raw material, probably hydrogen. How do you collapse that material without fusing it into heavy materials first? You would have to collapse it really quickly. Any fusion method stepped up 10 to 100 times might work for black hole generator. A containment breach of this would be really interesting to see. Would the engine collapse to a black hole or just explode all at once? I'd be curious to see. Okay, so after all that energy is somehow created, what do you do with it? Well, we have the hydrogen fuel as a propellant, which all ships have intake ports for, so we just need to apply energy to it and spit it out the ship to follow Newton's law. There are many ways to do that. We could shoot raw electrons at the propellant, like Hall thrusters, turning it into a cool plasma, and I mean cool as in temperature-wise, and then using electrical fields to push it behind the ship. Gives a little thrust, but is very efficient and doesn't require much propellant. This may not be the method used as the thrust is too low for a ship to take off from a planet, but it could work with a huge amount of power. Who knows? It's better for long-range probes that slowly accelerate over years, rather than for, like a fighter craft or something. You could instead pass an electric charge or an electric arc through dense enough gas to ionize it into a hot plasma. That's how a plasma cutter works, and it could have more thrust. The only problem is the electrodes tend to wear out and need to get replaced over time. And the gas has to be pretty dense for it to work. Normally oxygen is used, but oxygen and other gases can also damage the materials of your engine with this method. Or they could be hard to find, unless you contain it with magnets. Not sure how well nitrogen gas, especially the puny amount collected from space or atmosphere, would work with it, but maybe it might. You could also ionize the gas particles with radio waves or laser beams instead, and then use magnets and electric fields to expel the particles as a cold gas. That would be more powerful, but slightly less efficient, since you have to convert electricity to pump lasers first. We could use microwaves and lasers to instead heat the gas, or in a blade of solid, into a hot plasma, and then expel that, like the Vasimir system, either in continuous or pulsed form, and give it a push with magnets. That will give a lot more thrust, and slightly less efficiency, but a lot more thrust, which is generally what we're looking for. Finally, you could just run the gas through the heat exchanger of any of those hot generators I mentioned earlier, and turn it into a hot plasma like that, accelerating it and containing it with magnets. This would help cool the reactor and provide propulsion at the same time. The question is, how do you cool it when the thrusters are not running? Good question. The benefit of all these methods over chemical engines is that they're a lot more efficient, and you can just use just about any propellant for it, which means the ships don't need to carry all that propellant with them, and they don't need any oxygen. Just enough until they can refill in the atmosphere of any planet or moon. Although I'm not sure there is a significant hydrogen amount in the atmospheres of all moons or planets, so maybe it's just using any gases it finds, like nitrogen, oxygen, CO2, methane, who knows. They haven't really talked about it very much. So, one issue is some electric thrusters just have less thrust than chemical engines, unless you pass a ton of energy to them. So that's why they need fusion or fission reactors to power them. Mere batteries would not work. The plasma exhaust can also be contained and managed using magnetic fields, so they don't touch the sides of the engines, so there is less damage to the thrusters over time. You can even tilt the exhaust using magnets, so you need less moving parts when turning. Even the gas intakes can be collected and compressed with lasers and magnets, so you don't need turbines to compress them. All of these are benefits to the plasma engines over conventional engines. That's why they don't need a Saturn V setup for each ship. It doesn't have to be gigantic. There's a bit of hand-wavium going on though, but not horribly. So anyway, I hope this video helps. I am no astrophysicist or nuclear physicist, so if I've made any mistakes, you let me know. Go ahead, comment it. I'll update the video if necessary. But anyway, I was glad to make this video and hope it helped. Thanks. See ya. Bye.